We are back with another physics video today. I know it's been a while, but today we'll be tackling wave physics, which is section 3 as per the IGCSE physics syllabus. Um, Again, I'll be using the syllabus order, so do keep that in mind. Now, the first thing that the syllabus requires you to know, which is 3.1, is the general properties of waves. But before we even go there, I just want to touch on a few things first. We'll first be discussing the definition of a wave, and then we'll be classifying waves based on two things, and that will basically lay the foundation for the rest of the video. Right, so as you can see here, a wave is simply defined as a disturbance that conveys energy from one point to another. Now, there are two main things that you need to take into account here. The first thing is that it conveys energy. That is to say that it transfers energy and only energy. So, matter itself or the medium through which the wave is passing doesn't really get transferred. To put it into simpler terms, a water wave is basically transferring energy from the source of the wave to wherever the wave ends. So the water itself, yes, it is propagating, but the particles themselves aren't being moved by the wave. So that's a common misconception that you need to get out the way. It's also a disturbance, which I think is self-explanatory, and those are the two main things you need to take into account. Now let's look at the classification of waves, and there are actually two ways through which you can classify waves, those being the need for a material medium and the propagation of particles. Those are the two main ways of classifying waves. So the need for a material medium refers to whether or not the wave needs the material medium to convey energy. So under this, we have two types of waves. We have electromagnetic waves, also known as EM waves. Now, EM waves are waves that don't necessarily require a material medium. The key word here being necessarily. So yes, EM waves can convey energy via water or via air, but they don't really need the water or air, which is why EM waves can travel in a vacuum. And all EM waves travel at the speed of light, which is 3 times 10 to the power 8 meters per second square. Let's write that down. 3 times 10 to the power 8 meters per second. Sorry, not square, meters per second. And this is a speed that you need to know, especially for MCQs. And you'll understand why later on in the video. Now, there are different types of EM waves, 7 to be exact. And you do need to remember them, and you do need to remember them in this particular order. That's because as you go down, right, as I was saying, yes, you do need to remember all 7 types of EM waves, and yes, you do need to remember them in this specific order. That's because as you go down the list, the frequency of the waves increases, and we'll look at what frequency means later on in the video. But as you go up the wave, the wavelength increases. That is to say that radio waves have the longest wavelength but the smallest frequency, while gamma rays have the shortest wavelength but the largest frequency. And that's the basics of EM waves. Now, EM waves, as I mentioned, don't necessarily need a material medium. But there are other types of waves that do need the material medium to convey energy. So for them, a material medium is a must. And those are called mechanical waves. Let's just look at them real quick. Right, I forgot to mention, if you do have trouble remembering these 7 EM waves in order, an acronym that I like to use is this one right here. Roman men invented very unusual X-ray guns. As you can see, the first letter of this acronym, or this mnemonic, corresponds with the first letter of each of these waves, which is a useful way of remembering them in order. But any other method that works for you is also fine. The point is, remember the waves in this specific order. Right, so now we have mechanical waves. As I mentioned before, mechanical waves do absolutely require a material medium to convey energy, whereas the material medium was just an optional thing for EM waves. The best example for mechanical waves would be water waves and sound waves. Spring waves are also actually mechanical waves, which is basically saying if I have a spring and you apply a force at either end, it's going to move in some way or another. And those are waves, those are mechanical waves. And yeah, those are the most common examples of mechanical waves, and that's really the only thing you need to know about them. Now we come on to the propagation of particles, where you can subdivide them into two waves, those being transverse and longitudinal waves. Now, essentially, what this form of classification describes or distinguishes, it describes, it helps you separate waves based on how the particles vibrate. Now, what does this mean? Let's look at them more in detail. Right, so first let's look at transverse waves. Now, in transverse waves, the vibration of the particles is actually perpendicular to the wave motion, or you can say that the vibration is at right angles to the wave motion. And a few examples of transverse waves are water waves and all EM waves. Now, over here, you'll notice a peculiar thing. Before we describe the different types of waves based on the need for a medium, and we said there were EM waves and mechanical waves. Now, this is a completely different form of classification based on the propagation of particles. So what I mean to say here is that, as I was saying, what I meant to say was that under the need for a medium, waves can be either electromagnetic waves or mechanical waves. And on top of that, they can also be longitudinal or transverse waves. So a water wave, for example, is a mechanical wave based on this first form of classification, but it's a transverse wave based on the second form of classification. Electromagnetic waves, similarly, the electromagnetic waves based on the first form of classification, and there are also transverse waves based on the second form of classification. So it's not that waves have 4 different types. It's just that you can classify them based on 2 systems, and under each of these 2 systems there are 2 subsequent types of waves, which is a mouthful to say, but it's something you need to try and wrap your head around, and in order to avoid confusion during your exams. Right, as you can see here, I've drawn a wave diagram for a transverse wave, and all transverse wave diagrams have a shape similar to this. There are a few things that you need to note here. Number 1, this is the direction of the wave. So let's just say it's going to the west. You can see that the particles are vibrating at right angles to the wave motion, which is a characteristic of transverse waves. And you can represent the direction with this letter, obviously A, while the propagation could be B. Either way, you can see that it's perpendicular to the wave motion. And this applies to all forms of transverse waves. And that's about it for transverse waves. Now we'll look at longitudinal waves. Right, so longitudinal waves. Now longitudinal waves actually consist of vibrating particles, their particles vibrate parallel to the wave motion. Or you can also say that they vibrate in the same direction as the direction of the wave motion. Now what this means is that as the wave is moving in this direction, the particles themselves are also vibrating in the same direction. Now this leads to points of higher pressure and points of lower pressure forming. The particles are closer together and further apart. So areas of compression are these areas right here, where you can visibly see that the particles are close together, or that the wave crests are close together. You learn what that means in a few minutes. And you also have points of rarefaction, not refraction, rarefaction. I made a spelling mistake, just a second. Right, so there are also points of rarefaction, which you can also visibly see, and you can see that the wave crests are further apart. Points of compression have higher pressure, while points of rarefaction have lower pressure, and that's what the varying wavelengths show. I'm sorry, not the varying wavelengths, but that's what you can tell from the different points of compression and rarefaction. Now, the perfect example for longitudinal waves are sound waves. So let's just use that as an example for the rest of this chapter. But one thing that I want to mention here is that while yes, longitudinal waves are like this, you can represent them with crests and troughs, which I don't think I mentioned that before. But you can see here that over here I have a hill kind of on top and an upside down hill at the bottom. So this guy right here is called a crest. Let's just Right, as I was saying, this guy right here is called a crest, and this is called a trough. Let me just double check the spelling. Right, yeah, the spelling is right. It's not a good look that I have to look it up, it's fine. So you have crests and troughs. As I was saying, while yes, longitudinal waves do have this general diagram, most commonly you can represent this with crests and troughs, where you assume that the points of compression are the crests, the points of rarefaction are the troughs. So let me just show you how that works. Right, as you can see here, I've done what I previously described. I took the points of compression as the wave fronts and drew a transverse wave line accordingly. Now there are two things to note here. Number one, right after this, we will be looking at what wave fronts mean, since I've been saying that a lot, and that's something you do need to know. And number two, sound waves, or rather any longitudinal waves, are not the same as transverse waves. Rather, what this shows you is that you can display a longitudinal wave, such as a sound wave, in a form where you have the crest and you also have the troughs, and that makes it easy to find things like the period of the wave, or the frequency, or the wavelength. Speaking of all of those things, we'll be looking at them right now, as those are some general wave terms or features of a wave that you need to know as per the syllabus. Right, so the first wave term that I want you to know, this isn't part of the syllabus, but the first wave term that I want you to know is period, which can be represented using a capital T. So period is just the period of a wave is the time it takes. So it's the time represented with a small t that it takes to complete one vibration. So one vibration, or the total number of oscillations. Number of oscillations or vibrations, they mean the same thing, and this is represented with a small n. So the period is the time taken for a wave to complete one vibration. Again, this isn't in the syllabus, but it will make sense why I'm showing you this once we get to some things that are actually in the syllabus, because then you'll be able to understand how those formulas are derived. Now the next wave term that you do need to know according to the syllabus is frequency. Now, similar to the period, but not exactly, the frequency, represented with just a small f, is the number of complete vibrations of a wave per unit time. So it's n over t. You'll notice that f and t, or period and frequency, have very similar formulas. They're just inverted. So, okay, another thing, this time should always be in seconds. So there'll be MCQ questions that will involve you calculating the frequency. So you have to make sure that your time is in seconds. Again, your period and frequency are very similar in terms of the formula, and in a way you can say that frequency, which is n over t, is the same as, it's just the reciprocal of period. So you can say that frequency is t to the power minus 1, or period to the power minus 1. And very similar to this, you can also say that the period is the frequency to the power minus 1, or the inverse of the frequency. And this is just a really curious relationship that I wanted to point out. Right, I forgot to mention the units for each of these. The unit for periods is in seconds, because it is just a measure of time. It's the time taken for one complete vibration. Frequency, on the other hand, is measured in hertz. That's the hertz with a Z, and the symbol is Hz. Now, what that means is that 1 hertz is equals to 1 over second. But this part isn't really important. You definitely need to remember this and this. So that's the unit for both of them. That's the units for both of them. There are a few more wave terms. Let's look at those. Right. So number 3, the third wave term is displacement, which is just the distance that vibrating particles move from their resting position when a wave passes through them. While amplitude is what I would describe as maximum displacement, and the unit for both is in meters. Now, the best way to define and distinguish between both of them is via a diagram. So, as you can see, I have the diagram of a transverse wave here, or even a longitudinal wave, depending on how you draw it. PS, usually in IGCSE, I suppose the y-axis would be displacement, which is in meters, and the x-axis would be distance, which is also in meters. So the distance shows the distance shows how far the wave has traveled, while the displacement shows the propagation of particles, with the resting position basically being this line right here. So that's the resting position that we mentioned before. So if I have a particle here, as a wave passes through it, if I have several particles here, as a wave passes through them, they're going to vibrate and go up. Now over here you can see that there are varying forms of displacement. So I would say that here B and B, let's just call them B. These are examples of displacement. Let's say that the particles have moved up by 3 meters. However, there is the maximum displacement, or the particles that have moved up the most. Let's say that's 5 meters. So this is the amplitude. Essentially, they are the same thing. It's just that amplitude is the larger form of displacement, and that's and yes, while displacement isn't something that you need to know about as per the IGCSE scheme, amplitude is definitely something you need to keep in mind. And with that, we are done with I think about 2/3 of the wave terms. Let's just go through the last 3. Right, over here we have wavelength and wave speed, which are number, I think, 5 and 6 respectively. The wavelength is the distance that is covered by a wave in one period or one oscillation or vibration. Remember, a period is just the time taken for one vibration. So either way, a wavelength is just the distance that you cover in one vibration. Whereas the wave speed is the rate of change of wavelength per unit time. Now, the main thing that you need to take away here is the formula for wave speed. So you could say that wave speed, you could derive one formula for wave speed from its definition, which is wavelength over time. Or you could just say period, which is because period is a type of time. So wavelength can be represented using the symbol lambda. I think this is how you spell it. You don't need to worry about the spelling, but you do need to know this symbol. So lambda over period, where lambda, of course, is wavelength. Now you'll notice that this formula right here is the same as lambda over 1 times 1 over period. It's the same thing. I'm just writing it in a different way. And you'll also notice that 1 over the period is just frequency. If you can recall back to the first wave term that we looked at, I think that was the second wave term. So from here, you can see that the velocity, the wave speed, is lambda times the frequency, where obviously the frequency comes from this. And this is the main formula that you need to keep in mind during IGCSE. Right? So this is the In fact, I would argue that this is the only formula for wave speed that you need to worry about. This one is just a good way of figuring out how the second one is derived, but you'll never see questions involving this first formula. Rather, this second formula is very, very crucial, especially in paper 2, which is your MCQs. And that's about it for wave speed. Now we can finally talk about wave fronts and even rays, which I've been talking about a lot throughout the video. Right, as you can see here, I've basically drawn another wave diagram. So wave fronts and rays. Wave fronts are just parallel lines along a wave which represent the crest of the wave. That's important, and I'll come back to it later on. Rays, on the other hand, are lines that are drawn at right angles to the wave fronts. So they aren't really at a right angle, it's just compared to the wave fronts, they're drawn at a right angle. So you can see that here. The things in the red are the wave fronts, and the thing in the blue is the ray, and it's drawn at a right angle, and it shows the direction of wave motion. Wave fronts almost always have an arrow, as you can see at the end, and that shows that the wave is moving in this direction. I think rays are pretty self-explanatory. Wave fronts, you'll notice that wave fronts are only drawn at the crest or the peaks of the wave, and they're not drawn like this. That's because, as per the definition, they're only drawn at the crest. That's just a standard that we have adopted. It's also important to draw them only at the crest because the distance between two wavefronts is actually the wavelength, and this is something that you should know, especially for paper 2 and paper 4, because there are questions where they try and trick you by just giving you wavefronts. So the distance between two wavefronts is the wavelength, and wavefronts are only found at the crest of the wave, and that's more or less it. So that should kind of help. That should help with all the things that I mentioned before. And now I think we've built a very solid foundation for the following subtopics under wave physics. This is going to be a long video. Now finally we can tackle the namesake for this subtopic. Remember, we are still under the general properties of waves, which is like the first subtopic under wave physics as per the current syllabus. So under the first wave property is, the first general wave property for waves is reflection. Not in terms of light, though reflection of light is still something we'll look at later on, but reflection of waves in general. So reflection is just the sending back of an wave by, let's start again. Reflection is just the sending back of a wave by an obstacle when a wave incidents on an obstacle. So if I have something like, let's say, a mirror, and I have a wave, usually you can just indicate the wave by drawing an arrow with the wavefronts, and it incidents on the obstacle. So let's just do that properly. Right. So if I have the incident ray, so which is the wave that initially comes in contact with the obstacle, is going to get reflected at an equal angle to form a reflected ray. So let's just draw a better diagram to really get into the specifics of reflection. Right, so here we have a diagram representing a reflection. Let's just assume that this black body or obstacle is a perfect mirror. So when I have an incident ray, which is the ray on this side, you can see that there's an arrow to show the direction of travel, but when it reaches the obstacle, it is essentially reflected in the opposite direction, where you'll notice that there's a dotted line in the middle, and this dotted line is called the normal. Now the normal doesn't actually exist in real life, rather it's just an imaginary line. What does this mean? So when an incident ray basically incidents on an obstacle, it forms an angle. So between the normal and the incident ray, you have angle I, which is called the incident angle. And once this incident ray is reflected, to form the reflected ray, as you can see here, it forms another angle, now this time between the normal and the reflected ray. And the incident angle is actually equals to the reflected angle. So you can say that I is equals to R. And this is honestly the most important relationship under the reflection of waves. And you really need to keep this in mind pertaining to waves. Again, you'll notice that I didn't draw the actual waves. I simply drew the wavefronts because it's just easier and faster, and it's also a standard way of doing it. So that's more or less the only thing you need to know about the reflection of waves as a general property. When we start talking about sound and light waves, we are going to go more in depth. And now we come to refraction, which is going to be a little more complicated. Right, so now we come on to refraction, which is the second general property of waves. Now, I'll be treating this section to do three things. First, we'll be actually defining refraction, and we'll be looking at how it actually occurs. And then we'll also be looking at how refraction occurs in a water tank due to a change in depth, which is something that your syllabus specifically requires you to know. And I'll also be using this section to look at the reflection of water waves when they strike a plane surface in a water tank. I didn't do this before because I figured that I should cover all the water tank stuff together. So let's define refraction first. Now, refraction is the bending, or in other words, the change in the direction of a wave as it travels from one medium to another. So it's the change in direction of a wave that as it travels from one medium to another. Now, one very important thing that your syllabus requires you to know about refraction is that it occurs due to a change in the speed of the wave. So when the speed of the wave changes for any reason, refraction is going to occur. I've seen many questions in paper 4. Usually there are only 1 mark questions, but you can't afford to lose 1 or 2 marks that easily. So it occurs due to a change in the speed of the wave. And again, this is another thing you need to know based on the syllabus. Refraction occurs due to a change in the speed of wave. I've repeated that a lot of times. Now let's look at a water tank. Obviously, I have a water tank that looks like this. And let's say this is the water level here. You would call this area shallow water and then this area deep water. And let's just assume there's like a bit of a separation here. Obviously, the diagram that I've drawn here is a bit slanted to make it easier to show a few of the distinctions as refraction occurs. But the main thing that you really need to know is that as water travels from shallow water to deep water, it actually becomes faster. You'll also notice that it changes direction. So rather than directly going like this, it changes direction to move in this direction. So it would have gone this way, but rather it changes direction to go like this, which is why this is an example of refraction and not reflection. Another thing is that in this case, the small r represents the refracted angle. And you'll notice that the refracted angle here is a lot bigger than the incident angle. And what that means is that in reflection, the incident angle and the reflected angle were equal. But in refraction, that's not the case. Now, it doesn't have to be, or rather, the refracted angle doesn't have to be larger than the incident angle. But that's because if I were to reverse the directions, if I were to make it so that the water went from deeper water to shallow water, you would see that this would be the new R, and this would be the new I. And in this case, the incident angle is larger than the refracted angle. So it's not that it's not one or the other, it's just a matter of they are not equal, which is another difference between reflection and refraction. Another change that occurs is, remember, refraction occurs due to a change in speed. So in this case, as water goes from shallow to deep, goes from a shallow area to a deep area, its speed changes, and it's actually deeper. It's deeper in it's faster in deep water, and you can see this based on the wavefronts. So in shallow water, the wavefronts are very close together, whereas here they're very far together, which tells you that in deep water it's faster. Now, I always found it confusing how a larger wavelength or wavefronts that are further apart indicates a greater speed. Because in my mind, if there are more wavefronts, or if the wavefronts are closer together, that makes it look faster. But there is actually a reason for that. And that is also a good segue for me to come to the three, I guess, points that you need to remember as water travels from shallow to deep ends in a water tank. Right. So keep in mind that these 3 points only apply to water when it's going from shallow to deep. If you were to reverse the directions, if water went from deep to shallow, you would also the points would also be the opposite. So the first thing you need to know is that the frequency remains the same. So the frequency of the water waves in shallow water and in deep water does not change. It's the same. Let's just use the formula. So if I have V, recall that the velocity or the wave speed of a wave is frequency times lambda, or frequency times the wavelength. So frequency here, let's mark it in red. This remains the same. But as you go from shallow to deep water, the wavelength increases, which is just a fact we found out through experimentation. And an increase in wavelength can be graphically showed by a greater distance between the wavefronts, which is how you know that wavefronts that are further apart show that it's faster. So that should, at least if you can remember that, if you can remember this point and find out and remember the correlation between wavelength and wavefronts, you won't really get confused about the wavefronts. But the wavelength increases, and by proxy, even if the frequency remains constant at, let's say, 2 hertz, if the wavelength is increasing, your wave speed is still going to increase, and which is the third point here. And thus we can say that in deep water, water waves are faster. And now let's take a step back and go back to reflection, and let's discuss how water can reflect at a plane surface in a water tank. Right, so here you can see that I basically just used the reflection diagram before. Obviously, with so many wavefronts, it's kind of hard to really, there's no point in drawing the angles, but you can more or less make out that it's very similar in that the incident ray, which forms the incident angle against the normal, also gets reflected as the reflected ray, which again forms the reflected angle against the normal, at the incident and the reflected angle graphically you can make out that they are more or less equal, and that's just the basic principle of reflection. We are just applying it to water waves, so there's not much to really discuss here. And with that, I think we should move on to the third wave property, which is diffraction. Right, so now we have diffraction, which is the third wave property, or the third general wave property, and it's just the spreading of a wave as it passes through a narrow space or a narrow gap or over an obstacle. So let's do if you were to illustrate this second condition like this, you can see that in a practical sense, diffraction can be made use of with phone towers, where it's just depending on how you place the phone tower, you can just naturally ensure that the waves will diffract over an obstacle such as a hill to reach a settlement or to reach a house. So that's just a way that we use it in real life. In an examination point of view, the second part, the spreading of waves through a narrow gap, is much more important for you to learn, as it's also a lot more intricate, in the sense that I have two diagrams here, and you can see they both illustrate a wave it can always be a water wave or a sound wave or anything going through a gap. Let's call this diagram 1, let's call this diagram 2. In diagram 1, the gap is a lot bigger and the waves spread almost radially or as a circle. Whereas in diagram 2, the gap is in diagram 1, the gap was smaller, and in diagram 2, the gap is a lot bigger. And so the wave doesn't really spread as much, but you can still see it kind of takes like a plateau sort of shape. And with this, we can actually determine two factors that affect diffraction. Number one is the size of the gap. So diagrammically, that's not a word. In a pictorial sense, you can see that the smaller the gap, the more diffraction occurs, which is why in diagram 1, the diffracted rays are more arched than in diagram 2. And the second factor is the wavelength. So the longer the wavelength of a wave, the more diffraction actually occurs. So over here, the waves that I've used actually have a shorter wavelength. But if I had, let's say, a wave like this go through a small gap like this, you would see that the waves are spreading a lot. So wavelength is also a factor affecting diffraction. And to summarize the factors, the size of the gap is, to put it in layman's terms, the size of the gap is directly proportional to the rate of diffraction, and the wavelength is also directly proportional to the rate of diffraction. And based on this, again, sound waves, which have a longer wavelength than a lot of light waves, actually diffract more. So if I have, and this is an IGCSE question that came up a few years ago, but if I have, let's say, a corridor or a wall, I have person A here. This is going to really test my drawing skills. I have person A over here, and I have a bunch of people. Let me just quickly draw it. Right, as I was saying, if I have, let's say, person A and a marching band, let's just call them MB, marching band. Because light has a much much shorter wavelength than sound waves, person A won't really be able to see the marching band as he's on the other side of the wall or the other side of the building. But assuming that they're still playing their instruments, he will be able to hear them because sound has a much longer wavelength, so it's going to diffract or spread to the other side of the building. And we can actually observe this a lot in practicality as well, where, let's say, your parents are talking in a room and you're outside the room. You may not necessarily be able to see them, but you can still hear them because sound is diffracting more than light waves due to its longer wavelength. So this is diffraction in a very practical sense. And I also discussed how diffraction occurs through a gap. That is most commonly asked in the context of water waves in IGCSE, specifically, I would say, in paper 2. In paper 4, there have been questions where you're required to draw the waves after they spread, so you need to be mindful of the size of the gap. Let's go back and just look at it. If they give you, let's say, diagram 1 with a small gap, you need to be able to clearly show that the diffracted rays are spreading a lot, as in half circles. Whereas if the gap is large, you need to clearly show that they aren't spreading all that much, as in plateaus. So that's something you need to be mindful of in paper 4. Now there are technically two more general wave properties, known as superposition and polarization, but these are not actually part of the IGCSE scheme. Rather, if you decide to do physics in A levels, you're going to go into more detail about these two. So I'll just put those out there. You don't need to know anything about them. Right, so finally we've made our way to the second subtopic that's under wave physics, that being light waves. Now again I'll be breaking it down into three parts based on the syllabus, where we'll be looking at the reflection, refraction, and lenses. Well, there are more than three parts. So there's reflection, refraction. We'll be going a bit into lenses and how you can draw diagrams using them. And then there's dispersion of light, which sounds a little weird, but we'll also be looking at that. There's more or less light waves, and after that we'll be looking at the electromagnetic spectrum. Let's not get ahead of ourselves. So over here, then the first thing we need to look at is reflection, and this is reflection in the context of light. So as per before, the incident angle is the same as the reflected angle, and all the diagrams are very similar to what we've drawn so far. An application of reflection of light is through the use of a periscope, which is this diagram right here, where this is basically it's like a tube with two mirrors placed at 45-degree angles. And as you can see using the arrows, let's just draw the wavefronts as well. You can see that the light is reflected in a way where if person A is standing here, person B can somewhat view it, or view person A. It's one of the properties of light, reflection is a property of light that is used in many cases. It's also used in car side mirrors for obvious reasons, and many other purposes. The main thing that I want to look at under the reflection of light is the two types of reflection, which are best explained using diagrams. Right, so the first form of reflection is regular reflection, which is more or less similar to the diagrams that we drew before. But essentially, regular reflection occurs if this object right here, or if the obstacle rather, is shiny or very polished, such as a mirror. So let's just label it as such. This is a mirror. And the main characteristic of regular reflection is that if I have two parallel beams of light falling onto the obstacle, the reflected rays will also be parallel beams of light. So this is a little hard to explain, but the two incident rays here, which are the two red lines, are parallel as they fall onto the mirror, and when they are reflected, they remain parallel because this is a very polished surface. And accordingly, the law of reflection, where the incident angle equals to the reflected angle, is maintained for each of these. That is to say that for this first red line, this is the incident ray, and this is the reflected ray. Yes. Whereas for the second red line, this is the incident ray, and this is the reflected ray. So that basic law of reflection is still maintained. It's just that you're dealing with two parallel lines that also reflect as two parallel lines. I'm not sure if I made it more confusing, but that's the best explanation I can have. The real confusion, quote unquote, I would say comes with the second type of reflection, which is irregular reflection or diffuse reflection. So let's just draw a diagram for that real quick. Right, so the second form of diffuse reflection, as I mentioned before, is called diffuse reflection, which occurs mainly on rough surfaces, or not even rough surfaces, but quote-unquote normal surfaces, where light, if I have two beams of light, two incident rays that are parallel, and they hit a rough surface, they will be reflected, and they will be reflected following the law of reflection, which states that the incident angle and the reflected angle are equal, and that will be followed for both the rays. But the rays will not reflect in a parallel way. There's no way of really describing it verbally, and the best way to really see is through this diagram, where you can kind of make out that yes, the incident and reflected angles for both of the two instances of reflection along the rough surface is equal or are equal, but the reflected rays themselves aren't really parallel, unlike the incident rays which are parallel. So that's diffuse and regular reflections. And yeah, we are done with the actual concept of reflection, but now we need to look at a few more niche things that only apply to the reflection of light. Right, so this is the reflection on a plane mirror, and there's a lot to unpack in this diagram. So if I have, let's say this is your naked eye, right? It's just your eye, your normal eye. And I have object O that's been reflected on the mirror. So this is the real side, this is the mirror side, with I, of course, being the reflected object, the reflected image. Now, when you look at a mirror, you can see the reflected image. And the reason you see the reflected image is because this object is actually in its reflecting light waves of its own, which eventually make its way to the mirror and get reflected to your eyes. However, to us, without realizing it, it seems that this image itself is reflecting light waves and it's directly reaching our eyes. So, while the reason that we see this object in the first place is due to real waves or real rays being reflected by the mirror and reaching our eyes, but we perceive, rather, we think that we are seeing the image or the reflected image due to virtual rays directly reaching our eyes. And this essentially forms the idea of how, and this really just forms how we see images on mirrors. This is a really weird and weird diagram that we need to unpack. So feel free to take a screenshot and observe it as much as you can. And I suggest just taking it to your teacher and asking them to help you and help you to explain it. Yeah, more or less that's about it. Now we're going to discuss some of the properties of images that are formed on mirrors. And before we even do that, we'll discuss real images and virtual images and how they're different. Right, so I mentioned real images and virtual images. So the differences can actually be summed up very easily. A real image is one that can be produced on a screen. So I can actually put up a screen like this, or rather, yeah, I can actually put up a screen like this and produce the image on the screen, which is what happens when you use a pinhole camera. And it is formed by rays that actually pass through the object. So let's just draw a proper diagram. Right, so here you can see that my diagram isn't very perfect, but you can see that assuming that the image at the back, right here, right, as I was saying, assuming that the gray circle is the image, we can see that it's formed when real rays actually intersect with the object and eventually land on the screen. And again, this can be seen through a pinhole camera or real image, or the formation of a real image can be observed through a pinhole camera, and it's basically and it's obviously produced on a screen. So that's a real image. A virtual image is different in the sense that it cannot be formed on a screen, and it's produced by rays which seem to come from it. So this is what I explained before using the mirror. So images on a mirror are actually virtual images because we think that they're being formed by the virtual rays directly reaching our eyes, but however, they're being formed by real rays that are being reflected by the mirror in a way such that it seems that virtual rays are coming from it. It's really tough to explain, which is why I said you should definitely take your time and observe this diagram. So now we'll be looking at some of the properties of images that are formed on a mirror, which themselves are virtual images. So let me just write those down real quick. Right, so over here we can see some of the properties of images that are formed on a mirror. So number one, the images are laterally inverted. What this means is that in a mirror, left becomes right and right becomes left. So think about all the times you've stood in front of a mirror and raised your right arm. It looks like you're raising your left arm. That's because of lateral inversion. It's just a property of mirror images. And number two, the image that is behind the mirror is as far, the image that is formed is as far behind the mirror as you are away from the mirror. Basically, the image distance, which is the distance between the image formed and the mirror, we can call that V, is the same as the distance between you and the mirror, which is U. So U is equals to V, so image distance is equals to the object distance, which is the second property. The third property is the two distances are perpendicular to the mirror, so that's kind of self-explanatory. Number four, the image that is formed is the same size as the object. Again, this is self-explanatory. Think about all the times you've gone in front of the mirror. You don't look taller or smaller. You look the same because you are the same size in the mirror. And number five, the images are obviously virtual, which I explained a few minutes ago. And these properties are something that you need to know, especially for paper 4, I'm pretty sure. And thus we are done with the reflection of light. Now we can go to the refraction, which is the most confusing part of light waves. Right, so refraction of light. The principles of refraction pertaining to the general properties of waves that I established earlier in the video still apply here. And I'll be breaking this up into about 2 or rather 3, let's just say 4 different things. The first thing that we'll be looking at is real and apparent depth. The best way to, and the easiest way to explain this would be, think about a pool. When you go up near a pool, it doesn't look that deep, right? It looks maybe like 3 feet, but when you actually dive in, it might be 6 feet or 5 feet. So what you perceive as a shallow pool is the apparent depth, and the real depth is the actual depth, which is 6 feet. And this is caused by the refraction of light, or the change in the direction of light, which itself is caused by the change in the speed of light. So the real depth and apparent depth aren't the same, and you just need to know the difference between them. And by understanding this, we can start with the second thing under the refraction of light, or the second thing I want to look at, which is the refractive index. Now this is a very important property, or it's a very important concept. There are many MCQ questions on this, and it's often combined with a few more things that we'll be looking at later on, but this sets the foundation for understanding those. So refractive index is just the ratio, or if I were to give you a definition, is the ratio of the speed of the light in air through the speed of the light in a vacuum. So if you were to put this as a formula, refractive index, which is represented using a small letter n, is the speed of light in air. Let's just call that the speed of light in air, or the speed of light in a vacuum, which is 300,000 kilometers per second, or let's just simplify that to be 3 times 10 to the power 8 meters per second over the speed of light in the medium. Let's just call that x, the speed of light in the medium. So this is one formula for n. Another formula for n, which you'll see a lot more often, is n is equals to the sine of the incident angle, which is I, over the sine of the refracted angle, which is r. And obviously, since n and n are the same, you can say that this is equals to this. And there are questions where they won't outright give you the incident angle, and they might not give you the refracted angle, but they'll give you x, and you'll have to use the relationship between n is equals to n to find one of the angles. And remember how we discussed apparent and real depth? You won't see questions involving those in calculations all that often, but I will give you another formula for refractive index where n is equals to real depth over the apparent depth. So these are three formulas for refractive index that are very important. So the formulas themselves are the most important things that you need to take away, and the second most important thing that you need to take away is that they are all equal. Again, basically sin I over sin r is equals to real depth over apparent depth, which itself is equals to the speed of light in air, or a vacuum over the speed of light in the medium. And depending on what variables are given to you by the question, you can cross multiply each of them to find an unknown value. And most MCQ questions actually involve that itself. Now we can come to the second more complicated part, which has to do with critical of refraction of light, which has to do with something called critical angles, and consequently this will also help you learn about something called total internal reflection. Right, so critical angles. Critical angles are only really considered when light is traveling from an optically dense medium such as glass to an optically less dense medium. So if light is traveling from glass to air or from water to air, then you would eventually have to consider the possibility of looking at critical angles. Let's take glass and air as an example, focusing on diagram 1 first. When light travels from glass to air, some of it is reflected, as you can see from this one right here, and some of it is refracted from this ray right here. And as you increase the incident angle, so as you increase I, you're also increasing this refracted angle right here. And eventually you'll reach a point where the incident angle is so big, which you can see in diagram 2. So the incident angle eventually will become so big, if you increase it, that all of the light will be refracted, such that the refracted angle is 90 degrees against the normal. And this is known as the critical angle. So the critical angle is this angle right here, the angle at which the refracted angle is 90 degrees, which is a mouthful to say, but basically when the incident angle in the optically dense medium, in this case glass, that causes the refracted angle in the optically less dense medium, in this case air, to be 90 degrees is called the critical angle. Again, it's a mouthful, but that's the concept of a critical angle, and it's different in all cases. Now from here you can actually derive another formula for refractive index, where n, which is refractive index, is the sine of angle in air, because remember it's a formula for refractive index that we looked at before was sine of incident angle over the sine of refracted angle. So in this case we can see that the sine of the angle, let's just say sine of angle in air over the sine of angle in glass is equals to the refracted angle. Now when you reach a point where you need to worry about a critical angle, or not necessarily worry, you can say that n is equals to sine of 90, which is the angle in air, right? As you can see here, the sine of angle in air is 90 degrees. So n is equals to sine of 90 over the sine of the critical angle, which is the angle in the glass. And sine of 90 is obviously 1. So n is equals to 1 over the sine of the critical angle. And using this formula, you can find out the critical angle just by rearranging it. So this is another formula that we derive for refractive index. And now that we have considered critical angles, we can move on to total internal reflection, which kind of builds upon the concept of critical angles. Right, so total internal reflection. As I mentioned before, it essentially just builds upon the idea of critical angles, where in diagram 1, we considered a possibility where the incident angle is small enough for both reflection and refraction to occur as it goes from glass to air. In diagram 2, we considered a possibility where the incident angle is raised to a point where the angle of refraction is 90 degrees, and this incident angle is called the critical angle, and at this point no reflection is occurring. All of the light is being refracting. Now in diagram 3, we'll be looking at a possibility where the incident angle is increased even further, so that to the point where the incident angle is actually greater than the critical angle. And at this point, no refraction occurs whatsoever. Rather, all of the light is reflected within the glass, and this is just the process of total internal reflection. And this is actually applied in a physical way, or it has an application in fiber optic cables, where, let me just draw it real quick. If I have a fiber optic cable, this is a very rough drawing. It's made in a way such that total internal reflection allows that data is passed via reflection along the cable and none of the light is refracted. So via total internal reflection, data can be carried through a fiber optic cable. And again, just to reiterate, in diagram 3, which shows total internal reflection, the incident angle is greater than the critical angle, number 1. And number 2, none of the light is being refracted, it's just being reflected. This is different from number 2, where the incident angle is the critical angle and none of the light is being reflected, all of it is being refracted. And diagram 1 is a situation where both can occur and the incident angle is smaller than the critical angle. So with that, we are done with total internal reflection. Now we'll be coming on to lenses, which involves lots of drawing. Right, over here you can see that I've drawn the two types of diagrams for lenses. This first one is called a converging lens. While this one right here is called a diverging lens. Those are the names that IGCSE expects you to use, converging and diverging. So the main thing that I'll be focusing on is the terminology, even if that's not the most important thing. With lenses, I feel like it's best for you to simply get assistance from your teachers directly, since it involves a lot of drawing, and the main way to practice is, well, to draw them and practice. So I'll just help you with the terminologies, and that's all. The first thing that you'll notice is the capital C in both the lenses, with a central dot. Let me just put that in red. This is called the center of the lens, or the optical center. I've marked it in red. Yes. So the center of the lens, or the optical center, is just the middle of the lens. The next thing that I'll focus on is the capital F, the points marked with the capital F's. These are called the focal points, or the principal focus, and it's the point through which all the refracted rays of a converging lens pass through, or appear to emerge from in a diverging lens. The terminology there is very important, which is further collaborated by the focal length. So the focal length is the distance between the optical center and the focal point. Again, I'll trace back to what I said in the what I said about the focal point. In a converging lens, the focal point is the point where refracted rays they intercept, they intercept, which is self-explanatory based on the diagram. For a diverging lens, it's the point through which rays appear to be emerging. So you can see I have dotted lines here which show virtual rays. So virtual rays appear to be emerging from the focal point, even though you simply have normal rays that are coming to the lens and being refracted afterwards. Again, it's a complicated thing. It's best that you learn this in a physical classroom. I'm just doing my best to aid you with the terminologies. And the last thing here is the principal focus. The principal focus, or the principal axis, sorry, is the ray that passes through both the center and the focal point. So in this case, this is the principal axis, and here this is the principal axis. You can see that these two lines pass through both the focal point and the center of the individual lenses. And so I have done the best I can with lenses. Again, okay, I'll mention that converging lenses and diverging lenses can be used to correct short-sightedness and long-sightedness respectively. Right, as I was saying, long-sightedness can be corrected using a convex or converging lens, which is the one on top, whereas short-sightedness, which is what I have, can be corrected using a concave or diverging lens, which is at the bottom. And that's as much as I can cover from the syllabus. Ray diagrams, which are probably the most important thing about lenses, can only be done in a physical classroom or by you physically using a graph book. You should also know about the uses of magnifying lenses. Obviously, magnifying lenses help magnify images, but how that occurs can only be shown on a ray diagram. You should know that a virtual image is formed by diverging lenses, and it basically rays are extrapolated backwards, and they do not form a visible projection on a screen, which is more or less the characteristics of a virtual image. You should be, and if you do manage to draw ray diagrams, from the ray diagrams you should be able to figure out if the image is virtual or real, if it's inverted or upright or erect, if it's enlarged or the same size, etc., or if it's diminished as well. So those are some things that I can't really cover right now online. So you kind of have to do that on your own. Now, dispersion of light, which is the final part of light. Let's just look at that. Right, so dispersion of light. So dispersion of light is simply the process of separating visible white light. So this is white light. So it's the process of separating visible white light into its component band of colors. Now the colors are in this specific order: red, orange, yellow, green, blue, indigo, violet. You should remember this from checkpoint. As you go down the list, the frequency increases. The frequency increases as you go down the list, and this is possible because each color of light has, rather, the dispersion of light is only possible because each color of light actually has a different refractive index. So when you shine white light on a prism, each of its component colors, which have different refractive indexes, bend in different directions and change directions to different degrees, which is why refraction of light occurs. I actually made a small mistake in the diagram. Refraction technically occurs twice in the prism, so just a second. Right, as you can see, refraction actually occurs twice in the prism, once at point A, and the second time would be at point B. So it occurs twice. And yeah, that's more or less it about refraction. I will mention a few more things as per the syllabus. Monochromatic light basically describes a light which only has a single frequency, and thus it has a single color. You should also know that, as I mentioned, as you go down the list, frequency increases, but as you go down the list, wavelength also decreases, which is another thing that you should know. Right. Similar to how monochromatic light is a color of light which has the same frequency, you should also know that brightness of the light is basically reliant on the amplitude. So the larger, if two lights have the same brightness, we say that they have the same amplitude. And the speed of light is dependent on the medium. So if light travels in the same medium, it has the same speed, which is just the speed of light. Yeah, that's it with dispersion of light. Now we come on to, we reach sound waves. And technically in the syllabus, this is the point where they talk about the electromagnetic spectrum. But I believe we've already done everything that there is to do in the electromagnetic spectrum. We described the main regions of the spectrum. We know that they travel at the same speed in a vacuum. Right, the typical uses. So let me just say this, right? Radio waves are usually used in radios and television transmissions. They're used in RFID, which if you do ICT, you should be familiar with that. Microwaves are typically used for satellite televisions. And they're also used in microwave ovens, obviously, and mobile phones. Infrared is usually used for remote controls and also for electrical grills. And they're used for televisions, right? Remote controls for televisions and intruder alarms. Intruder alarms, thermal imaging, and televisions. These are honestly the most common things that come out in paper too. And usually, almost always, the answer is obviously infrared. So this, definitely take note of this point. Visible light is used in photography, obviously, and illumination. Ultraviolet is also used a little in security marking, but more often than not, it's used for detecting fake banknotes and sterilizing water. X-rays are obviously used in hospitals, and also they play some part in security, but not as much as the others. Gamma rays are used for sterilizing essential supplies such as medical equipment and food, and it's also used for the detection of cancer and its subsequent treatments. Now you should be aware of the harmful effects on people due to excessive exposure on electromagnetic radiation. So number one, microwaves can cause the internal heating of body cells. Infrared light can cause skin burns. Ultraviolet damages the surface of cells and can potentially cause skin cancer. So the sun actually emits lots of UV light to the earth. Luckily, we have the ozone layer to protect us. But the ozone layer is depleting, which is why we say it's a really big problem. And the last thing that you should know is that X-rays and gamma rays can cause mutations, which can cause cancer and can damage our cells, obviously. Right. As I mentioned before, communication with artificial satellites is mainly with microwaves, so keep that in mind. And yeah, that's more or less it with EM radiation. Right, so now we read sound waves. Now, we can pretty much speed run this part of the chapter since it's pretty similar to what you did in Checkpoint with a few minute differences. So number one, sound waves are generated from vibrating sources, or they're produced by vibrating sources. And they have different properties of pitch, loudness, and quality, which we'll look at later on. Sound waves, they can't travel in a vacuum, which implies that they are mechanical, and we obviously know that they are longitudinal, due to which we discussed way before, at the beginning of the video. The audible range of frequencies for humans is 20 Hz to 20,000 Hz or 20K Hz, and anything over 20,000 Hz is considered as ultrasound. Being longitudinal waves, they have points of compression and rarefaction, which represent higher and lower pressure respectively. And there's a question that I saw in one of the papers where it essentially gave you the diagram for a longitudinal wave, said it was a sound wave, and asked you why there were uneven spacing between lines. The real answer for that is because the uneven spacing of lines shows the variations in air pressure as the sound wave moves along, which you should keep in mind. As the frequency of another thing is that when the frequency of a sound wave increases, the number of compressions occurring in that same space also increases. You should be aware of echo. So let me just write that down. Echo. Right, as I was saying, echo. So echo is simply the reflection of sound. Is the reflection of sound in usually a closed area, but it can occur in open areas. You can use it to determine the speed of sound, which is an experiment that's defined in a lot of textbooks. But so I suggest that you just read those explanations, since they're usually very long. You can actually apply the use of an echo, or rather the reflection of a sound, in determining the depth of a sea or in medical imaging. Basically, there are often questions where they give you something like a ship, and let's say there's a rock here. It sends a sound wave down here, and the sound wave goes back up. And they'll usually try to trick you by giving you the speed of the sound, uh, and then they'll give you the time and ask you how far it traveled. In these cases, you use the formula V equals 2D over time, because it goes to the rock and then it comes back, which is why you use 2D. And you can apply the same formula to a lot of questions pertaining with the speed of sound waves. And speaking of the speed of sound waves, in air, the speed of sound is 330 meters per second. In liquids, or usually water, it's 1500 meters per second. And in solids, it's 5000 meters per second. As you can see, as you go from a gas to a solid, the speed increases due to the increase in density between each of these states of matter. Right. Now we come on to the actual properties of sound waves: pitch, quality, pitch, loudness, and quality. Right, so let's look at pitch and loudness first. So pitch is the quality of sound dependent on its frequency. So when you increase the frequency of sound, and that is to say, a sound with a high frequency and a low wavelength has a high pitch, and vice versa. Loudness has to do with amplitude, where the greater the amplitude of a sound wave, the louder it is, and vice versa. Now, the quality is a bit of a peculiar peculiar property of sound. Where it basically describes how a sound produced by two instruments, even if they have the same pitch and the same loudness, they're going to sound different. And this is because of the quality of the sound, which itself is actually dependent on the harmonics or the overtone of an instrument. That is to say, that the overtone itself is a combination of something called the fundamental frequency, or different fundamental frequencies, which are the smallest frequencies that can be produced in an instrument. Well, you don't actually need to really know much about quality, but it's good to have some knowledge about it. Right. And the last thing that I'll mention about sound is that in physics, sound is not the same as music, right? Sound is irregular notes, whereas music is regular notes. So they are not the same thing. And yeah, with that, we are done with wave physics altogether. Right. As always, guys, I hope you enjoyed the video. I hope you at least took something away from it. And yeah, that's wave physics. The video was a lot longer than I intended it to be. I'll do my best to upload a chemistry video a few hours after this goes up, but no promises. And I'll be honest, I'm not looking forward to making the next video for physics, because it's going to be on electricity and magnetism, and that is a lot longer than wave physics. I'm not really sure how I'm going to do that, but we'll see. At least this video should be out soon, and yeah, maybe consider subscribing if you like the video, and I'll see you next time.